Okay, good morning to everybody. The part 3, and in our previous lecture, we have discussed about the photoelectric effect and theory of special relativity. So today we will discuss the last part of modern physics. So in this part, we will discuss a photoelectric effect, and that means we are reviewing this and the Broglie wave, atomic spectra, the Bohr atom, and nuclear physics. First of all, we will start with what is black body. So first of all, we must know about the black body, then we'll start our topics. So first of all, what is black body? A black body is an ideal object that absorbs all the radiation incident on it and then radiates the energy. All objects emit electromagnetic radiation. Some frequencies can be seen, other can't be seen. And classical theory did not match experimental data, you must know. This is why we are depending on modern physics. And Max Planck theory of quantized energy also depend on this black body radiation. So first of all, what is black body? You must know what is black body. So in definition, we can define the black body. A black body is a perfect absorber of light at all wavelengths. That means we must know in light there are 7 colors. So and every colors have different wavelength. This is why all colors can be absorbed by this body. So this is the definition of black body, and it has some properties also. The Band's law: the peak wavelength of emission for a decreases as temperature increases. So Ben's law can be measured the properties of black radiation, and Stefan Boltzmann laws also. The power equals to black body, the power or energy of black body can given by this formula. You must know. Capital T is the actually temperature and power 4. So the Stefan Boltzmann law further defines an energy flux which is can be written by P by A, and this is equals to by previous law sigma T to the power 4. So hotter black bodies emits more total power per area, and properties of black body described principally by capital T, which is denoted by temperature. And the radiance radiated power as a function of wavelength and temperature, which is given by the Max Planck, with the Planck constant A is 6.63 into 10 to the minus 34 joules second, and K is the actually constant 1.38 into 10 to the minus 23 joule by per Kelvin. So a light bulb off and no light at any lambda. You must know there are radiance and different wavelength here given: ultraviolet, visible, and radio. So there is no light at any lambda. If the light bulb on, capital T equals to 3000 Kelvin, 3000 Kelvin, then the visible light will be in there, and dim in violet and blue, and fairly bright in red and orange. Okay, so the maximum we get 1000 nanometer. Okay, and So the combined brightness at each lambda, that means color, determines what color a BB appears. So black body radiations appears. So light bulb on T equals to 3000 Kelvin. Okay, this equals to red. And light bulb on, if T equals to temperature equals to 6000 Kelvin, then we get this diagram, which is visible maximum lambda for 500 nanometer. So in that case, the all color, four color equals to will be white color. And bulb on temperature equals to 30,000 Kelvin, then in that case we get this red one. And maximum wavelength lambda will be 100 nanometer. So in that case, the four color equals to will be this color. So the ultraviolet catastrophe, the classical thermal physics predicted definite flux and infinite intensity at a small wavelength. The solution will be given by Planck's hypothesis, and the electric resonators responsible for BB radiation, black body radiation, have discrete, that means quantized energy. So which is given by En equals to NhF, where S is the Planck constant, you must know. So now the photoelectric effect also can be explained with this. The photoelectric effect proposed on the particle model of light photons, the total energy of photon equals to SF, which can be written as NhC by lambda. And extension of Planck's work on molecular oscillator like this. So three electrons, and if light radiate on it, then we get the position of electron like this. So again, the position of light will be this. So, and next the electron will be moving. Due to movement of this, we get the electricity. And this is the actually photoelectric effect. So particle theory of light prediction, the frequency of light increases, the maximum kinetic energy of electrons also increases. So this equation is called actually Einstein photoelectric equation, and we have discussed in our previous lecture, where phi is the work function that holds the electrons to the plate. And if the frequency is less than f naught, that means cutoff frequency, or then this f naught can be denoted by phi divided by h, that means no electron will be ejected. Okay, so maximum electron energy as measured by the stopping potential, Bs, stopping potential, is independent of intensity. So in that case, for different wavelength on in nanometer and different frequency on 10 to the power 14 hertz, so stopping potential on y-axis, so there will be a slope h divided by Planck constant divided by E. So IR, if for ultraviolet ray and visible light and ultraviolet ray. So for example, we can calculate light shines on a substance with phi work function equals to 1 electric volt, and if lambda equals to 500 nanometer are electrons ejected from the surface. So find the energy of the photon. If we want to find out the energy of photon for lambda equals to 500 nanometer, which is given, you must know energy, total energy equal to hc by lambda. H is the Planck constant, you must know 6.673 into 10 to the minus 34 joule second, and c is the velocity of light, 3 into 10 to the power 8 meter per second, and lambda equals to given 500 nanometer, that means 5 into 10 to the power minus 7 meter. Okay, So we get the total 4.0 into 10 to the minus 19 joule total energy. So E equals to, we get electric volt, just dividing by 1.6 into 10 to the minus 19, uh, we get the energy in electric volt. So we get 2.5 electric volt. Now for a step two, to find out the maximum, we get the maximum kinetic energy 2.5 electric volt minus 1.0, because the work function when electrons not moving and staying in the matter before movement, the work function equals to 1 electric volt. This is why the maximum kinetic energy equals to 1.5 electric volt, which is greater than 0. So yes, electrons are ejected. If maximum kinetic energy is greater than 0, then we get the ejected electrons. This is a very important example for photoelectric equation. Now another important one, Compton effect. In 1923, scattered light has lower frequency than incident ray. Though Mr. Compton, a great scientist, he described this effect. Okay, so the scattering light has lower frequency than incident ray. So lambda is the wavelength and is the electron if is ejecting with different angle. One is theta and another is phi. So recall that relativistic energy equals to Pc, is the momentum for a massless particle. And the relativistic momentum for a photon is P equals to E by C, which is can be written as by A is by lambda. So in that case, we can describe the Compton wavelength, the lambda C. So this will be the equation for Compton wavelength. Now we can also find out the whether the energy, wavelength, energy and wavelength for this example, because we how much energy is lost by 1 mega electric volt photon that scatters off on electron with an angle theta equals to 60 degree. So you must know E equals to ASF, which is also can be written as AC by lambda, and is the Planck constant, and C, and this equals to 1.6 into 10 to the minus 13 joule, and lambda equals to 0.0012 nanometer. So lambda equals to can be found by the equation of Compton photon. So since the wavelength doubled, because 0.0012 nanometer and 0.0024 nanometer doubled, this is why the energy is also half mega electric volt. So 1 mega electric volt equals to, you must know, 1.60 10 to the minus 13, which is we calculated in our previous example. So now we'll discuss. So from this discussion, what is photoelectric effect? The photoelectric effect is the process of emitting the electrons from the metal surface when the metal surface is exposed to an electromagnetic radiation of sufficiently high frequency. For example, ultraviolet light is required in the case of ejection of electrons from an alkali metal. This is the figure which can be explained with the photoelectric effect. So schematic diagram of photoelectric effect setup is the electromagnetic wave is coming on electron in a evaporated quartz tube. So and then if the electron is ejected, then for the moving, due to moving of electrons, there will be produced current. So we can describe this apparatus after this experiment. An evacuated tube has two electrodes connected to the external circuit. The metal plate whose surface is to be irradiated acts as the anode. Some of the photoelectrons that emerges from the radiated surface have sufficient energy to reach the cathode despite its negative polarity, and they constitute the current. So this is the actually experiment. You must know about this from our previous lecture. So loss of photoelectric emission. There is no time lag between the irradiation of the surface and the ejection of the electrons. As a particular fixed frequency of incident radiation, the rate of the emission of photoelectrons, that is the photocurrent, increases with the increase. Photoelectric current does not occur at frequency less than threshold frequency. As the frequency above the threshold frequency, the kinetic energy of the ejected electrons depends only on the frequency of the exposed radiation and not on its intensity. So this is the loss of actually photoelectric effect. And this is the explanation I have discussed in our previous lecture. And there are seven discussion on photoelectric. So what is actually modern physics? The branch of physics which is based on the concept of quantum mechanics and theory of relativity. So there is actually classical physics and modern physics. There are two types of physics. So first of all, the classical physics, it is based on Newtonian mechanics and it consists of Newton laws of motion. In classical mechanics, velocity of any objects would be more and more less than velocity of light. And it's valid for microscopic objects moving with slow speed. Now, on the other hand, the modern physics, it's based on upon the quantum mechanics. It's valid for microscopic objects moving with extremely high speed. In molecule, in modern physics, velocity of any objects will be similar to the velocity of light. So it consists of theory of relativity and quantum quantum based theory. Okay, so you have to remember this: what is classical physics and what is modern physics, and what is actually the difference between these two physics. Now, what is in quantum theory? Uh, what is photon? According to Planck theory of radiation, according to the Planck theory of radiation, according to the Planck quantum theory of radiation, an electromagnetic wave travels in the form of discrete packets of energy, which is called quanta. Okay, one quantum of light radiation is called a photon. You have to remember this: what is photon and what is quanta. So characteristics of a photon travels with the speed of light. First characteristic, the frequency of a photon does not change on it travel from one medium to another. The speed of photon changes as it travels through different medium due to the change in its wavelength. Okay, the real mass of photon is zero. That is, the photon cannot exist at rest. So energy of photon can be denoted by E equals to H nu, you must know, or Hf. F is the lambda and H is the Planck constant, which is also given by Hc by lambda, where H is the Planck constant, lambda is the wavelength, and C is the speed of light. And momentum of photon can be found P equals to mc. Okay, m is the mass and c is the actually light of velocity, which is also given by P equals to, you must know, h lambda by c into and mc also is by lambda. This is why E divided by c. So, and Einstein mass energy relationship, you must know, equals to mc square. Equals to mc square is equivalent to the mass of a photon, which is given by equals to mc square and equals to a is nu. That means we can denote m equals to what? Mass equals to a is nu divided by c square or E divided by c square, same words. Number 8, photon are electrically neutral. Photon are electrically neutral and are not affected by electric and magnetic fields. In a photon particle collision, the total energy and the total momentum are constant. We have to remember that total momentum and total energy are constant. However, the number of photon may not be conserved in a collision. The photon may be absorbed or a new photon may be controlled. So photon energy is independent of intensity of radiation. You have to remember this. Now, what is the photoelectric effect? In phenomena of emission of electrons from a metal surface, when electromagnetic radiation of sufficiently high frequency are incident on it, is called photoelectric effect. The photo or light generated electrons are called photoelectrons. You must remember this. So for this, we can the study about the and this experiment study of photoelectric effect. So this is the experiment we have discussed in our previous slide. This is the experiment. So the effect of intensity of photoelectric field, the intensity of photon is proportional to photo current. The intensity of light and photoelectric current, the ratio will be constant. So that means proportional. If intensity of light increases, then photoelectric current also increases. So number 2, effect of potential on photoelectric current. At zero potential, the emitted electron are in random motion. Due to random motion of photoelectron, a small current constitute, that is, at zero potential, the photocurrent is not zero. You have to remember this. Second one, when potential applied to collector plate, that is positive, then most of the photoelectrons move towards it and constitute photoelectric current in the circuit. That is, photoelectric current increases with the increase in accelerating voltage. At some stage, for a current positive potential of plate A, all the emitted electrons are collected by the plate A, and the photoelectric current becomes maximum or saturated. If we increase the accelerating potential of a plate A further, the photocurrent does not increase. This maximum value of photocurrent is called saturation current. So saturation current means when all the photoelectron reach the collector plate A. So this is actually figure. This is the collector plate potential, and this is the retarding potential. That means negative. So stopping potential become from here minus B naught, and this is the zero origin to the photocurrent. This is the photocurrent. So increases, if the photocurrent increases, then intensity also increases from this figure. So number 3, when the potential applied to collector plate is negative, the electrons are repelled, and only the most energetic electron are able to reach the plate A. At a certain value of negative value B naught on the plate A, photocurrent becomes zero. This minimum negative potential B naught is called the cutoff or stopping potential, which is called B naught is the actually stopping potential. Effect of frequency of incident radiation on stopping potential. This is the B naught minus B naught 3, B naught 2 minus B naught 1. This is the stopping, and B1, B2, B3 for this is stopping. And saturation current, this is the collector plate potential, and this is the photoelectric current. Okay. So if radiation of some intensity I but different frequency lambda 1, sorry, gamma 1, gamma 2, gamma 3 are incident on metallic surface, then it is found that photoelectric current produced is same, but the stopping potential are different at different frequencies. Okay. Number 4, variation of stopping potential B naught with frequency lambda of incident radiation for a given photoelectric material. So cutoff frequency what? The minimum frequency gamma naught below which no emission take place is called as cutoff frequency or threshold frequency. When electron is not emitting, then their frequency will be denoted by gamma naught. So in that case, gamma naught can be denoted in graphically stopping potential. For stopping potential increment, the frequency of incident radiation will be there, and we observe that B will be greater than B naught. Okay, and B naught is this and B2 is this for metal A and metal B. So the failure of wave theory of light to explain photoelectric effect. Actually, failure of wave 3 of light to explain photoelectric effect. According to the wave theory, greater the intensity of radiation, greater are amplitudes of the electric and magnetic fields, and hence greater is the energy density of wave. So the maximum kinetic energy of photoelectro emitted must depends on intensity of incident light. However, particularly it does not happen. So incidence of maximum kinetic energy of photoelectron emitted on intensity of incident light cannot be explained using the wave theory of light. And these are also number 2 and 3. There are 3 failure of wave theory to explain photoelectric current. Also, whatever frequency of incident radiation may be, incident light of huge intensity over a sufficient time must be able to import enough energy to the electron so that they can get out of the metal surface. So threshold frequency must not exist. So this third one. Now the discuss briefly how wave theory of light cannot explain photoelectric effect. Okay, this is a question. Einstein explanation of photoelectric effect. Einstein photoelectric equation we have derived in our previous lecture. So according to the Einstein, when light is incident on metal surface, incident photons are absorbed completely by valence electrons of atoms of metal on its surface. That means energy will be S lambda S nu S or SF at each photon is partially utilized by an electron to become free or overcome its work function W naught, and rest of the absorbed energy provides the maximum kinetic energy of photoelectron during the emission. So S nu equals to half m b maximum b square plus W naught, where W naught is the work function when the photon is not emitting, and H lambda equals to energy of photon, and half mb square maximum kinetic energy of photoelectron. So what is the actually photo work function? The minimum energy required by the valence electron of an atom on the surface of metal to become free or to become a photoelectron. So W is the maximum energy work function. So at threshold frequency gamma naught, the frequency of photon A's gamma naught of incident radiation is just sufficient enough to liberate the electron, or just equal to a work function W. So W naught can be denoted by A's gamma naught equals to AC by lambda. So lambda equals to threshold frequency, remember it. So we can denote A's nu equals to half mb maximum b square plus A's gamma naught. So we can write maximum kinetic energy equals to Planck constant A's will be common. So gamma minus gamma naught. This is called Einstein's photoelectric equation. So at threshold frequency gamma naught, kinetic energy of photoelectron emitted will be 0. So if maximum energy will be 0 if this is equal. Okay. Now we can explain this explanation laws of photoelectric effect. As soon as electron absorbs energy of photon, it sets itself free. So emission of photoelectron starts as light fall on metal surface. And below threshold frequency, gamma naught frequency of photon is less than work function of metal surface. That is less than minimum amount of energy required to liberate an electron. So emission of photoelectrons take place only when the frequency of incident radiation is above or equal to the threshold frequency gamma naught. Further, the slope of graph between stopping potential V naught and frequency gamma E of incident radiation. Suppose this is the y-axis, stopping potential denoted by above 0 and V naught, and is the x-axis which is denoted by frequency, and below 0 there is a point A which will be the work function W naught. Okay, so there will be an angle theta inclined with the frequency, and another also theta equal. This will be reflex angle. So, and at this point B point, there will be a threshold frequency gamma naught, and at maximum distance, the frequency will be gamma. So we must know tan theta equals to perpendicular by base. Okay, base means what? Gamma minus gamma naught. Okay, and perpendicular will be this length. So this length you must know. This is the B naught. Okay, B naught. This is the B naught length divided by base. Base means what? Gamma minus gamma. So this equals to B naught equals to, you can denote in electric volt. Okay, electric volt. But in electric volt you can denote it by half m maximum kinetic energy, half m B square. So you must know maximum kinetic energy can be denoted by S into gamma minus gamma naught by photoelectric equation of Einstein. So from this we can write S by C. However, the intercepts of the curve of potential exists at minus OA equals to OB tan theta equals to what? B naught gamma naught S by C. That means OA equals to minus S. But if the graph is plotted between maximum kinetic energy EB naught of photoelectrons and frequency gamma of incident radiation, then the slope of graph is equal to height h, and the intercepts on the potential axis is at minus h b naught. Okay. Now number 3, as energy of photon depends on the frequency of light, so the maximum kinetic energy which the photoelectron is emitted depends only on the energy of photon or on the frequency of the incident radiation. As the number of photon of light depends on its intensity and one photon liberates one electron, so number of photoelectron emitted depends only on the intensity of incident light. Now, wave nature of matter. Actually, what is the wave nature of matter? You must know this famous scientist, de Broglie. So this is the actually hypothesis of de Broglie. He explained the wave nature of matter. So now we'll discuss the actually wave nature of particles, which is given by famous scientist de Broglie. That means de Broglie's wave. So nature of wave. A wave is described by frequency f and wavelength lambda, phase velocity u, and intensity I. So a wave is spread out and occupies a relatively large region of space. So nature of particle, you must know, a particle is specified by mass m, velocity v, momentum p, and energy E. A particle occupies a definite position in space. In order for that, it must be small. Okay? A particle generally very small. So now what is light actually? So interference and diffraction experiments showed the wave nature of light. So blackbody radiation and photoelectric effect can be explained only by considering light as a stream of particles. So in our previous lecture, we discussed about photoelectric effect and blackbody radiation also. So, so these two can be explained only by considering light as a stream of particle. If okay, so is light a wave or a particle? This is actually confusion for us. So what is light? In the historical background of light, in the late 1600s, Newton explained many of the properties of light by assuming it was made of particles. Okay, so it's true that from my theory, I argue that from corporeity of light, the waves of the surface stay generating water passing by the side of a broad obstacle which stopped part of them, bends afterwards, and dilate themselves gradually into the quiet water behaves obstacle, but light is never known to follow broad passes nor to bend into the shadow. So this is actually opinion of uh, Newton, Sir Isaac Newton. But because of Newton's enormous prestige, his support of the particle theory of light intended to suppress the other point of view. But Christian Huygens in 1678 argued that light was a pulse traveling through a medium, or as you would say, a wave. Okay? So there are historically, actually, what was light defined? Newton as a particle, but Huygens was at wave. In 1803, Thomas Young's double-slit experiment showed that much like water wave, light diffracts and produces an interference pattern. So in the 1860s, Maxwell, building on Faraday's work, developed a mathematical model of electromagnetism. He was able to show that this electromagnetism wave travels at the speed of light. This is actually development of quantum theory. And these are the four equations who compiled by the Maxwell. And this is the electromagnetic wave nature of light, which is electric, who both produce both the field, the magnetic field and electric field. So in 1900, Max Planck was able to explain the spectrum of blackbody radiator by assuming that light energy is quantized at quantum of light energy was later named a photon. So these two are the founder of this. And Max Planck also denoted this total energy of photon equals to H. H is the Planck constant, which is given by him, and F is the frequency. So a few years later, in 1905, Einstein used Planck's idea to explain the photoelectric effect, which is discussed in previous slide. And Einstein explained that the quantum of light energy seems particle-like. So in 1909, J. Taylor experimented with a very dim light source. His work and many modern experiments showed that even though only one photon passes through a double slit over time. So this idea given by Louis D. Broglie, lambda equals to h by p, where p is the momentum. In 1923, reasoned that if light waves would behave like particles, then particles should have a wavelength. Okay. So in that case, he also explained, uh, it was also supported by CJ division and Alice Garmer showed that electrons could produce interference patterns just like those produced by light. So, and on the other hand, Heisenberg uncertainty principle help us to examine the dual nature of light. You must know the electrons and other particles. That means wave nature and P equals to lambda by A. If we know the wavelength, we are certain about the momentum. But because the wave is spread out in space, we are uncertain about its position. So this is the wave nature and particle nature. Okay, we are uncertain about the momentum, but we are now more certain about position. Okay, this is given by Heisenberg. So photons striking a double slit one at a time produce interference. So if we observe which slit the photon chose, that means a similar experiment can be done with the beam splitters and mirror, which is called double slit experiment. So how can Alice and Bob know that their communication will remain private? Actually, there will be a digital or quantum system will be developed. Okay. So this famous scientist Louis de Broglie in 1924, French physicist graduated students proposed the idea that accounted for the fixed energy travels in Bohr's model. If waves can have particle-like characteristics, then can particles such as electrons have wave-like characteristics? So what he knew, actually electrons have wave-like motion because it's a particle. An electron had a restricted orbit. Each orbit had a fixed radius from the nucleus or a wide variety of wavelength, frequency, and energy is possible. Actually, he tried to know about this. So at the center of nucleus with radius r, there is actually there is a waveform of motion of electrons. Actually, no, there could be only allowed certain possible frequencies, wavelength, and energies in an atom. So de Broglie came up with an equation for the wavelength of a particle of mass m moving at the velocity v. So de Broglie's equation, this is the famous equation, de Broglie's equation, lambda equals to h divided by mv. Actually, lambda equals to wavelength in meters, and v is the velocity of meter per second, and m is the mass in kilogram, and h is the Planck constant, which is given by Mr. Planck. So what does this equation do? Actually, what are we using? Actually, there are four parts we are using: wavelength, Planck constant, mass of particle, and velocity, which tells us that all moving particles have wave-like characteristics. So suppose this food for thought: cars, basketball, do these have wave-like characteristics? Why or why not? This is actually a practical example for us. So yes, let's look at the equation. If lambda equals to h divided by mb, then the car and basketball do have a velocity and mass. Of course that. Using de Broglie's equation, we do get a wavelength for the movement of a basket and ball and a car. Let's try to calculate this one. Yes, mass of car, suppose 910 kilogram, velocity of car 25 meter per second. What is the wavelength of moving car? 2.9 into 10 to the power minus 38 meter. How big is this? Actually, can we see or measure this wavelength? No. Much too small to be detected, even with the most sophisticated equipment. So another one, electron speed 25 meter per second, electron mass 9.11 into 10 to the power minus 31 kilogram. What is the wavelength of the moving electron? Then we get 2.9 to 10 to the power minus 5 meter. Do you think we can measure this wavelength and see it? Of course, this is a very more and more less than the wavelength of car. So with the right equipment. So practice makes perfect. You must know what is the wavelength of an electron of mass. You must know 9.11 into 10 to the power minus 31 kilogram travels at a velocity 2 into 10 to the power 8 meter per second, 10 to the power 8 meter per second. And Planck constant will be this. So in that case, the wavelength will be 3.64 into 10 to the power minus 15 meter. Okay. So the circumstance of electrons orbit from the number 1 orbit to number 4 fourth orbit shown in a state like this. So from the de Broglie's equation, we came to know that actually lambda equals to h divided by p. So, and in the earlier days of Broglie's theory, the electrons in the main particle in concern. So we start our discussion with the electron. Okay, this is the actually de Broglie's equation. Now, cascade carrier postulate. In our previous slide, there's a postulate of state. Postulate one state that all particle motion are instigated by the photons or photon, be it electrons or any other matter. Okay. Now another carrier postulates of state. So and by the principle of the conservation of energy, the energy of moving electrons comes entirely from the incorporated photon. So the energy of the composition inside the photon will be this. So electron kinetic energy equals to photon kinetic energy will be same similar. Okay, which is given by the given equation, the half mv square formula. And for photon, this will be denoted by gamma, and for electron, it will be P. So this will be both are same. Now the momentum, you must know mass multiply velocity is equals to momentum. So moment of electron is the momentum of the electron, and m gamma c gamma square equals to Fs is the energy of photon. So this, if this is equal, then it will becomes twice multiply kinetic energy of photon equals to Planck energy of photon. Okay. So mv equals to p is the momentum of the electron. So this can be combined, and it's also can be denoted by velocity divided by frequency, okay, by ratio rule. This is the accordance with the principle of energy conservation. The photon is still vibrating at the same frequency. So the de Broglie equation, using this one, we can write the wavelength. If the wavelength lambda e, and the equation velocity of electron divided by frequency of photon gives us like this. So thus the de Broglie equation of wavelength lambda equals to h divided by p, where p is the momentum, which is proposed by the de Broglie in 1924. So summary of de Broglie particles, we can explain. This is the summary. An electron can move because of carrier particles such as photon or phonons. Okay? A moving electron is wave-like because of the oscillating carrier. The momentum of the electron is the momentum of the carrier. The kinetic energy of electron is the energy of the carrier. The wavelength of moving electrons is the shortened wavelength of the carrier because of the heavier electron. So, which is the summary of de Broglie's particle wave. And summary of the scaled postulates. Particles are moved by the carrier particles, mainly photon or phonons. The vibrating nature of the matter are due to the photons or phonon, as in the Broglie wave. Photons retains their vibration in free or bound state, leading to the principle of energy and momentum conservation in low energy cases. So this one, okay. So I hope everybody enjoying the de Broglie's wave nature. So now we atomic model and early models of the atom, Bohr's model of the hydrogen atom, and the quantum physics of the atom. Actually, the early models of the atom speculation about the microscopic structure of matter integrate people for thousands of years. It took until the late 19th century, however, before scientists started unlocking the mystery of the atom. In 1897, the English physicist J.J. Thomson discovered the electron, a particle with a negative charge and small size in size and thousands of times less massive than the smallest atom. The Thomson proposed that uh, uh, the atoms which are electrically natural have an internal structure that include both electrons and protons. So this is the Thomson model, and this is also the next. In 1909, the Ernest Rutherford gave his model, and after Rutherford, there are suggested another model after Rutherford. Then actually we get the Bohr's model, which is very important for us. So we'll discuss in a brief the early models of an atom. Okay. So, and it is very important for us Bohr's model of the hydrogen atom. First of all, we'll discuss some early models of the atom. So the first atomic model, the early model is John Dalton's model, which is given by the John Dalton. And solid sphere, this is he proposed his theory: atoms are very small individual and can't be divided or created or destroyed. An element is identical, different atoms equals different properties, and atoms of different elements combine to form compounds. So this is given by John Dalton. Next one, the plum pudding model, and the sphere is positively in charge. This is the atom, and whole atom is neutral because there are positive, same number of positive and negative charges in the model. He found that an atom consists of positively charged and negatively charged. An atom is electrically neutral because for positive uh, number of charge equals to negative number of charge. Negative charge electrons are fixed in the positive sphere. So it is given by Joseph John Thomson. So Sir J.J. Thomson also give this model, plum pudding model. Next one, nuclear model. Nuclear model, the structure of nuclear model is like this. So nucleus exists in the center of the atom, and movable electron moving in orbit, different orbit. Positively charged core also lies in the inside the nucleus. He theorized that atoms are mainly empty space. Positive charge is concentrated at the center of atom. The nucleus of the center of atom, the center of atom equals to the nucleus. Now, the electrons move around the nucleus, and it is given by Ernest Rutherford. Okay, so this nuclear model is given by Ernest Rutherford. Now, quantum mechanical model, which is given by Erwin Schrödinger. Erwin Schrödinger, and this model, quantum mechanical model, this is the figure out of atom and positive charge, low chance to find electron because at center there exists only positive charge, and high chance of finding electron beside the or outer space of electron. He discovered that electrons move around the nucleus in a cloud, not orbits. Okay, so orbits helps us predict the area where we can find electrons. The closer position to the nucleus, the higher chance to find the electrons. And this is the given by this model is given by the Schrodinger. So now the very important model, the actually planetary model, which is given by Niels Bohr. Actually, this is given by Niels Bohr, and this structure, this line is called energy shell or orbit, and electron is orbiting inside the orbit. He said that electrons orbit or move the nucleus. The orbit have specific size and energy. The energy is related to its size. The lowest energy is found in the smallest orbit. Electrons can move between each shell when gaining or losing energy. So this is the actually summary of uh, planetary model, which is given by Niels Bohr. Okay, and I will try to understand the Bohr's model of the atom. This is the biography of Bohr's model. And Bohr's models of atom, Niels Bohr, it's given by 1913, started that the light produced when atoms are excited by heat or electricity. Okay, so different from different elements or metals, he showed this. So Rutherford model could not explain why unique colors are obtained by atoms of the different elements. Bohr proposed that electrons are in orbits when excited, jump to a higher orbit. When they fall back to the original, they give off light. So Bohr's model, electrons orbit the nucleus like planet, and it's also called planetary method. Look like sun and Earth and different planets are moving um, around the sun. So this is why this model is called planetary model. And this is the carbon atom. There are 6 electron and 6 proton. So neutron also given by the orange color, and proton also plus and electron minus. So this is the Bohr's model of carbon atom. Now electron orbits the nucleus like planets like this. Each orbit can hold a specific maximum number of electrons. So this is the potassium, 19 electron here, 19 proton also, and 20 neutron. So orbit, there are 4 orbit and maximum electrons. First orbit in 2 electrons only exist, and second orbit in 8 electrons, third orbit also 8 electrons, and fourth orbit also 18 electrons. So so electrons fill orbits closest to the nucleus first. Now fluorine, 9 electron 9 protein, and it is its mass number 19. So number of proton equals to 9, number of electron also 9, number of neutron equals to 10. You must know, negatively charged. So draw the nucleus of proton. How many electrons can fit in the first orbit? Actually 2. And how many electrons are in left? So 7. So how many electrons fit in the second orbit? Only 8. So this is why the next, this is the electronic configuration of fluorine. Now you can try hydrogen, boron, and magnesium. Okay, boron this and magnesium also this. So Bohr summarize the model of hydrogen like this. The Bohr explained the line spectrum of hydrogen in below with a model in which the single hydrogen electron can only be in the certain definite orbits. In the nth allowed orbit, the electron has quantized orbital angular momentum will be n pi, and a is divided by twice pi, where a is the Planck constant. Recall that angular momentum is L equals to rp, where r is the distance from the center of atom and p is the momentum. And for a particle circular orbit, the magnitudes of momentum of nth orbit will be L equals to r radius multiply with mb, angular velocity. To get angular magnitudes of momentum will be radius multiply linear momentum. This equals to NAs. Okay, NAs. So S is the has its unit in momentum. Bohr's arguments is rather complicated, but with it he was able to explain quantitatively the spectral lines of hydrogen. So classical explanation of quantized momentum. One way to physical intuition about the quantized nature of atomic orbits consider wavelength equals to h by p and h divided by p equals to mb, which is a linear momentum. And it makes sense of electron due to their wave nature, uh, or to require orbits that are integral number of wavelength. As if they are standing wave, so we get this equation. And Bohr's result will be Rmb equals to Ns for nth orbit. Since the electrostatic force must supply the centripetal force, the electron in its circular orbit we have F equals to 1 by 4 pi epsilon naught E square by Rn. So this also can be written by mbn square by Rn. So combining these two equations allow us to solve simultaneously for Rn and Bn. So we get this. So Bohr's radius A naught equals to called Bohr's radius, and scale drawing of orbits and standing waves like this. So hydrogen spectrum in model details. This is the line spectrum at the bottom of the slide is not the entire spectrum of hydrogen. So it's just the visible light portion involving transition for n equals to 2. N equals to 2 means what? Second orbit energy state, and here n is the principal quantum number. So total energy will be kinetic energy plus potential energy. So we get this equation. So hydrogen like atoms, this is the explanation for hydrogen. So this is the actually distribution for hydrogen atom. Okay, and now we'll start another important part, radioactivity. This is the another important part of modern physics. So first of all, what is radioactivity? The plural number of nucleus of naturally occurring heavy elements like uranium, thorium, radium, and polonium are unstable and keep on emitting spontaneously invisible rays or radiation, and gives more stable elements. So these heavy elements are called radioactive elements. The property of emitting these rays is called radioactive of the elements. Now, okay, now the history of radioactivity. Actually, in 1897, Becquerel accidentally discovered the radioactive in pitch blende, a uranium mineral, while studying sunlight-induced fluorescence of various minerals. This mineral was found to produce a photographic image even through black paper. So this is the biography of Henry Anthony Becquerel, who is the father of radioactivity. Further experiments demonstrated that a mixture of charged particles and electromagnetic radiation are being emitted and are responsible for the effect of photographic film. So radioactivity and Curies, and you must know about the Pierre Curie, and so French physicist, Nobel Prize in Physics, 1903. And Marie Curie also, Polish or French physicist and chemist, got two Nobel Prize in Physics in 1903 and Nobel Prize in Chemistry in 1911. One and only female scientist of the world got two Nobel Prize. So she also studied the radioactive minerals, particularly pitch blend, which was more radioactive than the uranium extracted from it. So, deduced 1898 the obvious explanation, which blend must contain traces of some unknown radioactive components that was far more radioactive than uranium. So, this is the actually example of radioactive, that means polonium, actually according to the name of Poland, the native country of Marys. So Rutherford, the father of nuclear physics, you must know this nuclear physics, pioneer orbited the theory of atom and the discovered Rutherford scattering of nucleus of the gold foil experiment. First, you also discuss about the half-life. So Rutherford gold foil experiment, this is the summary of that experiment, transmitted beams, little or no deflection, scattering beam, small deflection, and scattering beam, large deflection. And this is called gold foil experiment. Now radioactive materials undergoing nuclear decay reaction violated the idea that atoms are the unchangeable and individual ultimate building blocks of matter. Additionally, experiments with cathode ray tube accelerators and mass spectors eventually showed atoms do consist of small components, proton, neutron, and electron. So some important terminology for this is the nuclear reaction, regular chemical reaction, and atom. Uh, So elements, you must know what is elements, the simplest stable or building block of materials, isotope, an atom of element with the same number of proton, and radioisotope, radioisotope, an unstable isotope that undergoes nuclear decay, radiochemistry, the study of radioisotopes. So you must know about this nuclear notation, that is the actually atomic number, and is the mass number, and x is the n elements. This is the helium, 4 is the mass number, and 2 is the atomic number here. So this is the example of isotopes. Carbon 12, 12 is the mass number, 6 is the number, atomic number, and carbon 13 also. So how many electron and proton, neutron here? You must know from here. So this is the summary of electrons or isotopes. Okay, now the radioactivity. Is the nucleus of an atom of an element which spontaneously dis distinguish to emit alpha, beta, or gamma ray. The ray emitted by radioactive elements are called radioactive rays. The phenomenon in which the nucleus of atom of the elements undergoes spontaneous or uncontrollable disintegration or decay, emit alpha, beta, or gamma rays, is the process of spontaneous disintegration of the nuclei of heavy elements with the emission of certain types of radiations. So emitted alpha, beta, gamma rays from the unstable nuclei are called ionization radiations. Depending on how the nucleus loses and accesses the energy with a lower energy atom of the same form will result, or a completely different nuclei and atom can be formed. So what is ionization? Ionization is the addition or removal of an electron to create an ion. Ionization radiation is any type of particles, alpha or beta, or electromagnetic wave gamma, that carries out energy to ionize or remove electrons from an atom. These radiations are of such high energy that when they interact with the materials, they can remove electrons from the atoms in the material. This effect is the reason why ionizing radiations is hazardous to health. So radiation of it damage to DNA. You must know DNA means deoxyribonucleic acid. This is the figure, and double strand break base loss due to radiation, and DNA cross linkage, protein cross linkage, single. So actually there are two types of radioactivity. One is natural and artificial radioactivity. So natural radioactivity is the process of spontaneous or without external means by itself the disintegration of the nuclei of heavy elements with emission of radiation. These are unstable nuclei found in nature. So the element whose nuclei spontaneously disintegrate are called radioactive element. For example of natural radioactivity are this: uranium 238 becomes thorium 234 and helium 4. And thorium 234 becomes polonium 234 and 1 electron. So radium 226 also become 222 thorium and helium 4. So what is natural? All heavy elements above atomic number 82, above 82 show the phenomenon of radioactivity. The emission of radiation changes the structure of nuclei and transforms the atom into a higher atom. The heavy elements are unstable, therefore they disgrade, disintegrate to acquire more stable. Since the radioactivity is practically affected by temperature, pressure, and other conditions, so we conclude that it is a nuclear property. Therefore, alpha, beta, particle, and gamma rays are emitted from the nucleus. It may be noted that electrons revolving around the nucleus are not responsible for radioactivity. So, what is artificial radioactivity? And it is the process in which a stable or non radioactive nuclei is changed into an unstable nucleus by bombarding it with appropriate atomic projectile like alpha, neutron, or proton. So, this is the example of artificial radioactivity. Aluminum plus helium become phosphorus and 1 neutron, and boron plus helium becomes isotope of neutron and plus nitrogen and neutron, and nitrogen 13 becomes carbon 14 and 1 electron. So this is the difference between two radioactivity. One is natural and artificial radioactivity. So this is very important for you: natural radioactivity and artificial radioactivity. So natural radioactivity is the spontaneous. Since it is natural radioactive, the nuclei of heavy atom disintegrate on their own accord, forming slightly lighter and more stable nuclei and emitting alpha, beta, gamma radiations. And artificial radioactivity is not the spontaneous, since in it the nuclei of the atoms have to be bombarded by fast moving particles like alpha, neutron, proton, and deuteriums. And secondly is uncontrolled. Natural radioactivity is uncontrolled, and hence it cannot be slowed down or accelerated by any means. Secondly, artificial radioactivity can be controlled by controlling the speed of bombarding particles used on bringing about the artificial radioactivity. Thirdly, natural radioactivity is usually shown by heavy elements, but artificial radioactivity can be induced even a light element, that means less than 82 atomic number. So units of radioactivity, the standard unit of radioactivity is Curie. And what is Curie? Curie is defined as the mass of radioactive elements which produces 3.7 into 10 to the power 10 disintegrations per second. Okay, this is the important units in radioactivity. Uh, Equivalent dose is a dose quantity representing the stochastic health effects of low levels of ionizing radiation on the human body. It is derived from the physical quantity absorbed dose, but also takes into account the biological effectiveness of the radiation, which is depend on the radiation type and energy. The SI unit of measure, so Siebert. Okay, equivalent dose SI unit what? Siebert. Now, gray. To measure absorbed dose, the amount of energy actually absorbed in some material and is used for any type of radiation, and any materials that does not describe the biological effects of the different radiations. So gray equals to joule per second. 1 joule of energy deposited in 1 kilogram of a material is called gray. So we have to remember this one. Now, Ronzant is used to measure exposure, but only to describe the gamma and X-ray, and only in air, are equals to depositing in dry air enough energy to cause 2.58 into 10 to the power minus 4 coulombs per kilogram. So this is the unit of Ronzant. Ronzant equivalent man, to derive equivalent dose related the absorbed dose in human tissue to the effective biological damage of the radiation. Actually, to damage the cancer, you have to use X-ray or different gamma ray. Now, CBAR, to derive equivalent dose, the absorbed dose to human tissue of the effective biological damage of the radiation. So 1 CBAR equals to gray multiply Q. Q is the quality factor unique to the type of the incident rays. Now, what is the Becquerel? It is used to measure a radioactivity, the quantity of a radioactive material that have one transformation per second. So Becquerel equals to one transformation per second. There are 3.7 into 10 to the power 10 Becquerel in one Curie. You have to remember it. So one Curie equals to 3.7 into 10 to the power 10 Becquerel. Now, detection and measurement of radioactivity. The radioactivity of the radioactive substance is detected and measured by the instrument like this. George Molar counter, Wilson cloud chamber, scintillation counters, and dosimeter. So this is the George Molar counter and this machine to detect radioactive. And this is the scintillation counters. This also used to measure radioactive, and dosimeters. This is also used to detect radioactive. Now, types of radioactive rays. There are three types of radioactive rays. One is alpha, beta, and gamma. From the very beginning, we must know about this. So, what is alpha? Alpha ray. An alpha particle is a helium nucleus whose mass number is 4 and nuclear charge atomic number is +2. Alpha particle decay. For proton rich heavy nuclei, a possible mode of decay to more stable by an alpha particle emission. Now, alpha decay has largest ionizing power, ability to ionize molecules and atom due to largeness of alpha particle, has lowest penetrating power, ability to penetrate matter, skin, even air, protect against alpha particle radiation. This is actually properties of alpha decay. Now, alpha particle, when a radioactive element emits an alpha particle, the mass number of the daughter element is decreased by 4 units and atomic number gets decreased by 2 units. That means polonium 215 becomes 211 um, lead. That means 4 decreased by 4 units, and helium also decreased by 2 units. Now alpha decay, this is the example, unstable atom, Y also more stable atom, and helium also alpha particle. This is called alpha particle, remember it. This one is called alpha particle. Okay. So alpha decay, from radium 226, we get radon 222. That means 4 reduction. That means 4 decreased by 4. Atomic number, mass number decreased by 4. And increased by and decreased in helium. This is also an example of alpha decay. Example of alpha decay: radium transformed to radon and helium, and radon also transformed to another element Y with mass number A and atomic number Z. Helium is alpha ray. This is also alpha ray. Radon becomes polonium and alpha particle. So alpha decay, this is also thorium and alpha ray, and uranium 234 becomes thorium 230 and alpha particle. This is the also example of alpha decay, lead and helium. So what is the beta decay? A beta particle, denoted by beta, is a fast moving electron which is emitted from the nucleus of an atom undergoing radioactive decay. Okay, beta decay occurs when a neutron changes into a proton and electron. So a neutron changes into proton and electron is called beta decay. So many neutron rich radioactive nuclides decay by changing a neutron in the parent nucleus into a proton and emitting an energetic electrons. So beta decay, as a result of beta decay, the nucleus has one less neutron but one extra proton. The atomic number Z increases by 1 and the mass number A stays the same. So beta decay, many different names are applied to its process: electron decay, beta minus decay, negatron decay, negative electron decay, negative beta decay, or simply beta decay. So there are different forms of name of beta decay. Now this is the example of beta decay. Polonium becomes a astatine with a beta particle. Okay. So beta decay, this is the example of similar example of alpha decay and beta decay. X become Y and beta particle. So for example, polonium 218 becomes radon 218 with beta particle for beta decay. So thorium also becomes vanadium 234 with beta particle. So this is the lead, um, and this is also example for beta decay. Now comparison between a beta particle and electrons, both particles are negatively charged, which is equal to -1. And number B, when the atom loses an electron, a cation of the same element is formed. On the other hand, when the nucleus loses a beta particle, new neutral element is obtained. So now what is gamma decay? Gamma rays are not charged particle like alpha and beta. Alpha is the positive and beta is the negative. So gamma rays are electromagnetic radiation with high frequency. When atom decays by emitting alpha and beta particles to form a new atom, the nuclei of the new atom, there are two nucleus. This is why nuclei, okay, plural of nucleus. Atom form may still have too much energy to be completely stable. This excess energy is emitted by gamma rays. Gamma rays photon have energies of approximately 1 multiplied 10 to the power minus 12 joule. Now what is gamma rays are electromagnetic wave or photons emitted from the nucleus or center of an atom. The gamma decay, what will be the gamma decay? Very often a nucleus that undergoes radioactive decay is left in an excited energy state. The nucleus can then undergo a second decay to a lower energy state by the emitting proton. Proton emitted in the waves is called gamma gamma rays. This is the example. Absorption absorption of gamma rays. Many nucleides emit gamma rays of more than one wavelength. If gamma rays of alpha are selected, the absorption of exponential fraction of the absorption thickness I equals to I naught e to the power minus mu d. So here I is the intensity transmitted by thickness by a thickness of absorber. I naught is the intensity of the gamma rays incident on the absorber, and mu equals to the line linear absorption coefficient or attenuation coefficient of the absorption unit will be per meter. Gamma rays passing through a absorber like this. So I naught is coming to absorber and emitting as Ix, starting with 0 and passing distance x. So also hold for x. So absorption I equals to I naught exponential e to the power minus mu x. So note that the absorption of rays increases with the atomic number of materials of the absorber. The exponential nature of gamma ray absorption arises because in most cases a gamma ray quantum loses all its energy in a single event, and therefore the fractional intensity beam falls by a fixed amount of each time. So this is the total linear attenuation coefficient for different factors mu, and this is the least for and coefficient. Now photon emission, actually gamma rays coming from the center of nucleus, and X-ray also coming from electrons. So difference between X-ray and gamma ray. This is the So what is X-ray? X-ray are electromagnetic wave or photon emitted not from the nucleus, but normally emitted by energy changes in the electrons. These energy changes are either in electrons orbit shells that surround an atom or in the process of slowing down, such as in X-ray machine. The properties of alpha, beta, and gamma ray. There are three types of radiation here. You must know alpha ray, radiation, beta, and gamma. So this is the actually nature will be this charge will be plus 2, minus 1, and 0 gamma ray, and mass will be relatively mass very small beta and no mass because gamma ray. So speed slow, fast, and speed of light, ionization, ionizing effect strong, weak, and very weak. This is the difference properties of alpha, beta, and gamma rays. Now, the radiation penetrating ability, this is the alpha particle like this, and beta particle like this, and gamma ray more powerful and emitted uh, through the body. So, other important particles here, you must know positron decay. This is the positron decay. Nuclei that have too many protons for stability often decay by changing a proton into a neutron. In this decay mechanism, an anti-electron or positron beta plus or electron with loss of proton. So a neutron nu are emitted. So positron decay, this is the example of positron decay. And neutron decay, another one is neutron decay. A few neutron rich nuclides decay by emitting a neutron producing a different isotopes of the same parent element. So this is the example of neutron decay. And proton decay, a few proton rich radionuclides decay by emission of proton. Okay. In such decays, the daughter atom has an extra electron. So this extra electron is subsequently ejected from the atom's electron cloud to the surroundings, and daughter returned to an electrically neutral atom. Daughter means actually newly produced proton. There is the example of proton electron capture. In the quantum mechanical models of an atom, the orbital electrons have a finite probability of spending some time inside them. So this is the electron capture example. Also, this is the general electron capture decay radiation written as this. And this is also example, iron and barium becomes manganese 55 and 131 respectively. So some important particles, deuteron and triton and neutrino. This is also another important particles. For example, one thorium disintegrate gives lead 206 as the final product. How many alpha and beta particles are emitted during this process? So if this for solution, if the number of alpha and beta particles which are emitted from thorium is x and y respectively, then the formation of 206 lead can be represented like this equation. Okay. So thorium becomes 234 minus 4 multiply x, because 4 will be subtracted, and 90 same. So after solving, we get y equals to 6. The 7 alpha and 6 beta particles are emitted. Now another one, this is another example. Exercise this, you can solve similarly. So this is exercise 2 and this is exercise 3 left for you. Exercise 4 also left for you. So exercise 5. not disintegration constant or decay constant. Suppose a radioactive elements A at time t equals to 0 by will be n naught. Disintegrate into another substance B. Now as the time pass, the element A disintegrates and hence the amount of A goes on decreasing while that of B goes on increasing. So we are finding actually decay constant. Suppose after, so suppose after t time, the amount of A left disintegrate by n. So the remaining amount of amount will be n naught minus n is the amount of A that gets disintegrated into B after time t. So now if a small amount of dn of A gets disintegrated into B in a small time dt with the change of time t, then the rate of disintegration of A into B is equal to minus dn dt. Minus will be is used because decreasing. This is why amount decreasing, which is proportional to the amount of A left undisintegrated n. Okay, so the decay constant can be written as negatively dn dt, rate of change of amount n which is decreasing is proportional to n. So this equals to removing proportionality, we use constant k, where k is called decay constant and k means what is the amount of proportionality which is called disintegration or decay constant. So minus dn by n, we can write from this equation, minus dn by n equals to k dt. This is very important equation for you. Now decay constant can be defined as the fraction of total amount of the radioactive substance dn by n, which is disintegrate in unit time. K is expressed in time per second, okay? Per second or per minute or per hours, per days or per years. Now integrating equation 1 over limit and not and n for the and time will be 0 to t. So integrating on both sides and not to n and 0 to time. At time 0, the amount was what? N naught. After time t, the amount become, after decreasing, capital N. This why 1 by n 1 by x formula integration what? Ln x. Okay. This why ln n by n naught equals to minus kt. So n by n naught equals to e to the power minus kt, and capital N equals to n naught e to the power minus kt. Actually, here k is the decay constant. So radioactive decay kinetics or plot from variation of n as a fraction of time t for different time t starting the amount of particle will be n naught after time t decreasing n naught, okay, decreasing n naught, and at time t amount is capital N. So lambda n equals to a and lambda n naught equals to n naught. So decay constant and half life ln n or a, so we can write t half is the half life. So in next slide we'll discuss about half life. So what is half life? Half life is a radioactive nuclide is the time taken for half the nuclei present to disintegrate. Disintegrate means what? Radiation, okay, reduction of atom with time t. If the half life is represented by t half, then small t equals to t half, n equals to n will be what? Number of atom will be half n naught by 2. So therefore by equation n equals to n naught e to the minus k t will be what? T half equals to 0.693 by k, where k is the decay constant. So half life of uranium will be like this. This is the important of half life. So half life of uranium will be 4.5 billion years, and thorium half life will be 24 days. Uranium will be 2,45,500 years half life. So thorium will be 75,000 years, and radium will be 1,600 years. So very interesting.
So radioactivity, uranium-238 radioactive decay series. This is the decay series, and alpha decay and beta decay at a time. So there are many isotopes which has different half-life and decay constant. So uranium will be 4.5 into 10 to the power minus 10 to the power 9 years. Very high half-life will be uranium. So this is the activity. Activity is the rate of disintegration in a radioactive substance. Activity of substance I equals to minus dN by dt. The minus sign shows that the activity decreases with the passage of time. Now, this is proportional to the number of present atom. Okay, so removing constant can A equals to can. So we can find some example. Yes, for example, one a sample of radioactive materials contains 10 to the power 18 atom. The half life is the materials 2000 days. Calculate the fraction remaining after 5000 days and activity of the sample after 5000 days. Exercise, this is the exercise left for you. Okay, exercise 11, and this left for you. Using any book, you can solve this one. Okay, there are isotopes. We have discussed about this, the definition of isotopes and example. Chlorine 35 and chlorine 37. Same number of atomic number is called isotopes. This is the example of isotopes: carbon 12 and carbon 14, and lithium mass mass spectrophotometer, weighing atoms, and separation of isotopes from uranium 238 and uranium 235. We get two main isotopes. Characteristics of isotopes, very important for you, since the atomic number of isotopes are same. They contain the same number of proton in the nucleus and the same number of electrons revolving this. Since the mass number of isotopes are different, the sum of proton and neutron, the nucleus is also different. So this is another characteristics. So 5 types of isotopes: radioactive isotopes or unstable, non-radioactive isotopes. This is the example of non-radioactive isotopes. Uses of radioactive isotopes in medical field. Okay, very important for you. In medical field, we have to use isotopes in order to find out the blood is circulating to be a wounded or not. Radio tracers is introduced into the body, and after suitable time, some quantity of blood is taken from the wound, and its radioactivity is measured by means of George Moller counter. George Moller counter detects the exact position where the blood clot in that human body. In medical field, we also diagnosis of disease. We have to use radioactive or isotopes. So this is the single photon emission computed tomography, an image produced by PET scanner during diagnosis. Bone scan also image produced by PET scanners is also uses of isotopes. This isotope with high energy gamma ray has been used for the treatment of cancer. The treatment of disease by use of radioactive isotopes is called radiotherapy. Okay, the uses of linear accelerator for the treatment of different kinds of cancer. Treatment of cervical cancer using high dose rate intraarticular. Okay, and treatment of prostate cancer. We have also used isotopes. And sterilization and irradiation. In agriculture, we have to use different isotopes. In agriculture, radioactive materials are used to improve food crops, preserve food, and control insect pest. They are also used to measure soil moisture content, erosion rates, salinity, and efficiency of fertilizer uptake. Application of radiation during protection of agricultural materials. So potato, this is the main food for us. So gamma rays attack food and bacteria dies. And gamma rays to the strawberry and also bacteria dies. And in environment, we have to use isotopes. Radioactive materials are used to tracers to measure environmental process, including the monitoring of silt, water, and pollutants. They're used to measure a map influence and pollution. In industry, we have to use radioactive materials. Used radiography, civil engineering, materials analysis, measuring devices, process control in factories, oil and mineral exploration, and checking oil and gas pipelines for leaks and weaknesses. We have to use radioactive materials or isotopes. So examples in the uses of industrial measuring devices which contain radioactive materials are they are used for testing moisture and content of soils during road construction, and this is also use this is also detector sensitive to smoke detectors. Okay. And other application of radioactive isotopes, many satellites use radioactive decay from isotopes with long half-life for power, because energy can be produced for a long time without refueling. The isotope carbon-14 is used by archaeologists to determine age. This is the exercise for you. Mm, and factors affecting nuclear stability. This is the 5 factors: magnetic, magic number, binding energy, packing fraction, neutron to proton ratio. And this is exercise for counting proton, neutron, and electron. Nuclear reaction, you must know there are reactions in which element is converted into the other by emitting alpha orbital particles. This is the difference between chemical reaction and nuclear reaction, very important for you. I hope everybody will understand this. So nuclear fission is a nuclear reaction in which a heavy nucleus, when bombarded with slow moving neutrons, split into two nuclei of near equal mass with the release of anomalous amount of energy. This is the example of nuclear fusion. Uranium 235 adding with neutron becomes barium and curium. 4 parts. Okay. So here is the thermal neutron. B is the fission, and C is the fission product, and D is the huge amount of energy. So to produce huge of energy, we have to use nuclear fission. Types of nuclear fission, there are 2 types: uncontrolled and controlled. Uncontrolled or explosive fusion reaction will be this: from uranium 235 neutron, we get there are 4 parts. So nuclear reactor or atomic reactor. Uses of nuclear reactor. This is the uses of nuclear reactor. Uses of nuclear reactor for the product of electricity. And you must know in our country, Rupur nuclear plant have been established. So to get more electric energy, and in next year we'll get, I hope, this energy. So nuclear fission, also called atomic fission, and this is example for isotope 2, isotope hydrogen 2, and hydrogen 3. Hydrogen A is actually called deuterium, another isotope of hydrogen, and B is the tritium, C is the alpha particle, D is the neutron, and A is the anomalous amount of energy. So nuclear fission can be figured out like this. Our sun undergoes a nuclear fission. This is the example of our sun. Okay. Now nuclear fission and nuclear fusion. Fusion and fission. So there are two. It has different difference. Nuclear fission, from one we get more isotopes, but nuclear fusion we have to add different two or more uh, uh, atoms of radioactive elements. This is the exercise distinguish between nuclear fission and nuclear fission. Give some equations to support your answer. This is the atomic bomb in Japan, which was used by USA in 9th August in Nagasaki and in 6th August in Hiroshima. So you must know this is the first and atomic bomb was dropped. So atomic bomb in Japan, this is the very and atomic bomb in Japan before and after this. This is the actually figure of destruction of atomic bomb. Uh, the effects of atomic bomb you must know for more radioactive effect. Nowadays in Japan, and nowadays in Japan, so the periodic table for different elements you must know after 82 heavy metal produces alpha ray. And so thanks for you. Now quiz, this is quiz for you. So half-life of a radioactive substance is time interval during the half of a given number of radioactive nuclei decay and half remains there. So this is the example of thurium becomes panium and beta particle. So this is the table for half-life and radioisotopes formed. Decay series in of uranium 38 we have also discussed it, and this is the also we have discussed. This is very important equation for exponential behavior of number of and this is the mathematical expression we have proved this one. And radioactive decay t half equals to 0.693 by lambda, and n equals to n not half to the power n. Half life in general n equals to 1 2 3. So this is the example. So graphically we can plot the equation of radioactive uh, and decay constant. Decay constant also decay rate r is the number of decay, and this is also radioactive measures of radioactivity. 1 becquerel equals to 1 decay per second. 1 curie equals to 3.7 into 10 to the power 10 becquerel. So this is the example for you, very important example. Okay, thanks to everybody. Now, an important example, the half-life of a specific element was calculated to be 50 to 100 years. Calculate the decay constant. Okay, recall ln2 equals to 0.693, you must know. So k equals to 0.693 divided by t half. So t half equals to actually 0.693 and time t half equals to 50 to 100. So we get 1.33 into 10 to the power minus Fourier. Similarly, you must know we can use this equation ln n not by n kt t equals to t half equals to half life, where n what is calculating lifetime other than the half life. How would you calculate the t34 or t78? Okay, just using this equation we can find out this one. Okay, t half equals to ln2 by k, and ln2 means 0.693. So